Now we're going to be starting a fun unit. We're going to be talking about polynomials. So today we need to do an intro to polynomials. We need to understand what they look like. We need to understand the basic vocabulary about them. And then we need to know how to do operations with them, like adding and subtracting and multiplying. And the reality is that those are all things that we've been doing since probably elementary school, if not pre-algebra, right? So let's talk about first polynomials and what they look like. So you can see here, um, we have a bunch of types of polynomials here. So I just want to walk through them one at a time. I'm going to start with the most basic. I'm going to start with a constant polynomial. And a constant polynomial, the example that I have here is just that it's y is equal to 3. So it's just y equal to a number. Are you guys okay with that? So I'm going to say that the general form for the constant is going to be y is equal to a. Are we okay with that? Okay, so then in pre-algebra we start focusing focusing on linear equations, right? And graphing them and all these things. Well, a linear equation is a specific example of a polynomial. And you can see here that you have the example y equal to 2x minus 5. Okay, and normally we would write that in the form y equals mx plus b. I'm going to let that go away. Do you guys see that? Okay, but because I'm trying to write ultimately larger polynomials that can be of any degree, um, what I'm going to do is this. I'm going to write it as y is equal to ax plus a. Now, sometimes we'll do ax plus b, right? But I'm going to do ax plus a. But the problem is if I just leave it as a, what happens is that means that if a is 2, then it would be 2x plus 2, right? Or if a is negative 10, then it would be negative 10x plus negative 10, right? Because the a says that it has to be the same. But what I can do to help differentiate between the two a's is I can add to its name. And so what I'm going to put a subscript in. That's a number that's just down a little bit to separate those two a's. So I'm going to say this one is a to the 1, a sub 1. I've got a reason for doing that, and that this one will be a sub 0. Now, why did I choose 1? Because this is x to the first here, right? Why did I choose 0 for this one? Well, technically, right, this would be x to the 0. Because remember, what is x to the 0? What does x to the 0 equal, you guys? Yeah, it equals 1. So, and isn't it nice, right? Then this matches the degree that's here, right? This one matches the degree that is here. So I'm going to go back and I'm going to modify this first one to be a sub 0. Okay? So you can think of it, right, like A is a last name. And so you can talk about Labus all you want on this campus, right? Come to my home, can't call me Mr. Labus anymore because there's 2 other Mr. Labuses in our household, right? Or you can't just call me Labus, like the cool way of, right? You're going to have to use my first name to distinguish me from my sons, right? You have to use my first name to distinguish me from my wife and my daughter. Does that make sense? And that's what that subscript is like. It's like a first name. Okay? And then keeping it as a show that they're a part of a family. Notice here, right? The reason I did x to the 0 here, or a to the 0, is because technically I have x to the 0 power. Okay, do we need to write the x to the 0? And the answer is no, right? I'm making a point so you understand why I'm writing what I'm writing. Okay, are we together? Okay, so watch this. So then in algebra 1, we start focusing then on quadratics, right? And then I have an example of a quadratic here, y equal to x squared minus 3x plus 1. And you learn that the standard form is ax squared plus bx plus c, right? Well, as we're doing polynomials, instead of a, b, and c, we're going to use a, and a, right? But we're going to use subscripts to help separate it. So we're going to have here, so y equals a, right? Now, it's going to be ax squared, so I want to do a sub 2 x squared plus, and then a sub 1 x. Do I have to write to the first power? Well, no, but I'll write it here just to make the point, and then plus a sub 0, and you can see that I'll write in gray because we don't normally want to write this, the x sub 0. Is this helpful? Do you guys see that? Because I'm going to lead to something that's super confusing, but it won't be, I don't think it's going to be confusing because of how we're going about this, but I need you to understand this general form that we're doing here. Are we all together? Okay, I see heads shaking. Okay, so now we're in algebra 2. We're going to start graphing things that have a higher power than a quadratic. So this is a cubic here, where the highest power is a 3, and so, or higher. And so you can see, right, I could add another variable and do, right, A, B, C, and D, right? But again, we're trying to show relationships. So I'm going to write this as y equals, now the highest power is a cubic here, so it'll be a sub 3, x to the 3, plus a sub 2, x to the 2, plus a sub 1, x. I'm not going to put x to the first anymore. Is that okay? And then plus a sub 0. I'm not going to write the x to the 0 because I think you guys understand where I'm pulling everything. Got that? Now here's what's kind of cool. Is like when we're talking, you'll hear me talk about the quadratic term. The quadratic term would be the term that has a power of 2. Got it? Or I might say the linear term. Well, that would be the term that is a to the 1 x. Or the constant term, that would be a to the 0. Or the cubic term, right? That would be the a sub 3x to the 3. So how are we doing on those general forms that I just came up with? Because now I need to show you the ultimately confusing formula. And a lot of teachers start with this. I used to start with this, and it just used to be so confusing to students. But I don't think it's going to be confusing to you guys now, but well, here we go. So let's come down here. So the general form of a polynomial, I'll just say of degree n. Right? So if I say of degree n, that means that my highest power is going to be n, an unknown. Got that? So let's write the general form. So it would be y is equal to, and it would be, if the highest power is n, then it would be ax to the n. So it would be a sub n x to the n. Does that make sense? That will be the first term, the highest term. Are we all cool with that? So what would the next term look like? Didn't we just subtract 1 every time, you guys? So this was 3 and 3, this was 2 and 2, this was 1 and 1, this was 0 and 0, right? So if it's a sub 1 x to the a sub n x to the n, then what would the next term be? A sub n minus 1 x to the n minus 1 plus. Okay, and then I'm going to do dot, 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 because then the reality is the next term would be a sub n minus 2 x to the n minus 2. And then it would be a sub n minus 3 to x to the n minus 2. Get the idea? Okay, and then I'm going to keep adding, and I want to go down until I get a sub 2 x to the 2 plus a sub 1 x plus a sub 0. Now, does that mean that we have to have more than 4 or 5 terms? Because I have an a to the second, x to the second, a to the first, x to the first, a to the 0, a sub 0, sorry. And the answer is no, right? Remember that all of these up here are examples of polynomials. So a constant is a polynomial, a linear is a polynomial, a quadratic is a polynomial. So we don't have to have a quadratic term. I just put it in there so you can see how it's going to land, right? Because oftentimes polynomials are powers higher than 2 or 3. Are we together? Okay. Is the general form as overwhelming as it can feel? No? Yes? Okay. Okay, so you can see here, I have this statement now. It says where all exponents are non-negative integers. Uh-oh. Okay, wait. So, non-negative, what in the world does non-negative mean? Okay, not negative, right? What numbers are not negative? It's obvious. You can state the obvious answer. Huh? Thank you. Positive, right? Okay, but there is actually one number that is also not negative, that's also not positive. Good job. Look at that. So it's 0, right? Or positive numbers. So not negative is just a way of including 0, right? Because normally we just say positive numbers, but 0 can be a part of it, and so therefore we have to make sure we include that. And then integers. What are integers? They're numbers. Okay, what kind of numbers are they? Huh? Okay, so whole numbers, every whole number is an integer, right? It's a good way to describe a good portion of the set of integers. Whole numbers, so that means there's no decimals, no fractions, right? Okay, and then there's one other aspect of integers that we should make sure we include, and that's what they have a sign, right? They can be positive or negative, right? But obviously here we're saying they're not negative numbers. So let's just say here integers means that there is no decimals or fractional. Now remember we're talking about exponents here. So we're only going to have positive numbers in the exponents or 0, and there will be no decimals, decimal or fractional exponents. Okay, so examples of polynomials, and I have this huge blank here. And the reason why is because I already gave you a bunch of examples. So I'm going to just say here, C above. I am going to write a few more, but I'm going to say C above because all of these up here, right, are polynomials, and they were all examples of polynomials, so I don't need to rewrite them. Notice that I could do this. I'll write a few more. So let's say that because all of these had all their lower, like if it was x to the first power, like here it was x to the first, and then it was followed by a constant, and then we had a second, a first, and a constant, and then we had a third, a second, a first, and a constant. But there's nothing that says you have to have every single place represented. So let me give you an example here, like y equal to 5x to the 100 power plus 10. So notice here, right? This is, I could rewrite this to be y equals a sub 100 x to the 100, right? Because I know that they're going to match, right? The subscript and the exponent. And then it's plus, and it's just the constant. So what is a sub 100, you guys? What's a sub 100? That's in this position right here. What's a sub 100? Isn't it the 5? You guys see that? But here's the question. What's a sub 99? Is there a x to the 99th power? No. There's not an x to the 99th power that we can see. Why? Because what's the coefficient? What's the number that you multiply times x to the 99? Wouldn't it be 0? What's 0 times x to the 99? Isn't that just 0, you guys? Okay, keep that in mind. I'm going to get rid of that. What's a to the 98th power? 0 again. Good. I'm starting to see people catch on. So I can keep going, right? What is a sub 0 going to be? 10. Good job. Now we're on it. Okay. Are we okay with all the examples of polynomials between the ones that we have up above and the one that I just did that had missing terms? Okay. Are we good? Okay. Let's take a look here at examples of things that are not a polynomial. Okay. So here, this first one, I have y is equal to x to the 1/2 plus 8x. Why is this not a polynomial, that first one? Why is this one not a polynomial? Good, you can't have fractions as exponents, okay? So I'll just say here it's not an integer. I'm going to do the one below it now. Let's go to that one. This one here, why is this one not a polynomial? What was that? Okay, we have a negative exponent, an exponent that's a negative. Okay, exponent is not non-negative. Okay, and then in this last one, I'll tell you, see here how we have an x in the denominator? That means there's a negative exponent on it, basically, if it's in the bottom. It's on the whole expression, x plus 3, but ultimately the variable is a part of that. Okay, are we okay? Can we keep moving? So let me bump this up here. So degree of a polynomial with only one variable. Hang on. So the degree of a variable in only one variable is the highest power on a variable. And I'm going to write in capital letters on a variable. The degree of a polynomial with two or more variables. What if if it's in one variable, you just look for the highest power on a variable. But if it's two or more variables, so meaning it has an x and a y. So the first one, it only has x's, right? Now the second one, it has x's and y's. What do? So, and I like to focus on one variable in this class, but I'm going to tell you, you find the sum of each term's exponents. Exponents on variables. The term with the highest sum is the degree. Okay, so we're going to go through some examples down below. But if I give you, x to the third plus x to the fifth plus x, right? What's the highest degree in this one? 5, because that's the highest power on a variable, right? For this one, right, if I give you x to the second, y to the third plus x to the fifth plus y to the sixth, right? Well, what's the degree of this first one? Well, you would add the 2 plus 3, so its degree is 5. You see that? The degree of this one is 5, so there's 2 that match, and the degree of this one is 6. So what's the degree of this expression? And it would be 6 because that's the highest. Clear? So if there happens to be two variables, you add the exponents of the terms. Okay, so leading term and leading coefficient are super important to this unit. Degree is also, and degree in one variable is actually the most important probably. So the leading term is the term with the highest degree. The leading coefficient is the coefficient of the leading term. Remember, the coefficient is the number in front of the variable. Okay, let's look at the problems down below because that's where I'm going to work on making sure we understand the different terms. Okay, so terms. Terms are separated by addition and subtraction, right? So if we look at number 1 here, that's this one right here, how many terms do I have? How many, you look at the addition subtractions and they separate the terms. Bless you. How many terms do we have here, you guys, in number 1? 4 terms. Good job. So we have the minus 6x, we have the plus 7x squared, the minus 8x cubed, and the plus 1. So let's figure out the degree first. Oh, let me write 4 terms here. So what's the degree of the minus 6x? What's the power on the x? There is no power that we see. We know that means it's a 1. So the degree of the first term is a 1. What's the degree of the second term? 2. Good. What's the degree of the third term? What's the degree of the last term? Good. Because remember it's x to the 0. So its degree is 0. So the degree of this polynomial is the largest of those numbers, which is the largest? 3. So then what's the leading term? It's the term that has the degree of 3, by the way, the highest power. So what's the leading term? Isn't it the minus 8x to the third, right? It includes the coefficient, it includes the sign in front. Got it? So what's the leading coefficient of the leading term? What's the coefficient on the leading term? -8. Good job. If you put it in standard form, it just means that it's written from highest degree to lowest degree. So I'd put the -8x to the third first, and then I would put the quadratic term if there is a quadratic term. Is there a term that's to the power of 2? And it's the x squared. Is there a term to the first power? It's the minus 6x, and then the plus 1. Let's go to number 2. There we go. How many terms are there for number 2? Looks like there's 4 again, right? 1, 2, 3, 4. So what's the degree? I'm going to come in really close here. What's the degree of this first term? The 7x cubed y. Ooh, how did you get 4? It's correct. Good. Y has the exponent of 1, x has the exponent of 3, and you add the 3 and the 1, and you get 4. What's the degree of the second term? Just 2. And then the third one, we're going to have to do some adding again. Isn't it going to be 1 plus 2? Which is 3. And then the last one, 5 plus 2, which is 7. So what's the highest degree of each term? It's 7. So the degree is 7. The leading term is going to be the term that has that degree, right? So it's the plus 10x to the 5th, y to the 2nd. So I'm just going to leave it as positive. And then what's its leading coefficient? 10. Now, to put this in standard form, usually what you do is you pick a variable and you write it in descending order for that variable. In this class, I'm going to focus on making sure that you can do that. For one variable, I'm not going to focus on two variables. So I'm going to skip just putting it in that form here. Got it? Does that make sense what I'm doing? So it means on the test, if I ask you to put it in standard form, that it'll be in one variable. Okay, number 3. How many terms do you see in number 3? So I'm going too fast here, aren't I? How many terms? 2 terms? 1, 2. Good job. 2 terms. What's a problem? Do you guys see any problem here? Ah. Can a polynomial have a negative exponent? So I'll say here, negative exponent on a variable, which we do know how to work with, but it's not a polynomial. So therefore, not a polynomial. Okay, so I'm going to skip then finding the degree, leading term, leading coefficient, because we are only working with polynomials with those terms right now. Last one, how many terms? Looks like 4, right? 1, 2, 3, 4. So I want to find the degree. Now this is only in one variable, so that's nice. What's the degree of the first term? Good, it's x, so it's x to the first, its degree is 1. Degree of the second term is 7. Degree of the third term is 3. Degree of the last term? Is it 8? It's a trick question, isn't it? It's how I like to try and trick you on the test. It's x to the 0, so it's 0. So let's do this here, right? Careful. Degree is not 8, right? Okay, so what's the highest of those powers? 7. So the term that falls on is that negative 4x to the 7th. The leading coefficient is the negative 4. By the way, this we already said it had 4 terms, so I'll just write here 4 terms. If we write it in standard form, highest power is to the 7th. I would start with that, so it'd be negative 4x to the 7th. What's the next highest power? Good, it's to the third power, which is the 8x to the third. The next highest power, that minus 10x, right, the x to the first. And then the last is the 2 to the 8. Okay, are we good with vocabulary? Okay, the next section, total, like just information you already know, so we just have to make sure we know it. Adding and subtracting polynomials. It's so straightforward. I only have one example, okay? And you can see here, is this right here a polynomial? The 7x to the fourth minus x to the second minus 4x plus 2. Yeah, all its exponents are integers. They're positive, right? We're good to go. How about this one here? Is this one a polynomial? Yep. Okay, and notice that I am subtracting them. Got it? That's the operation between them. So when I go to do this problem, I'll just take the parentheses off the first one. So this becomes 7x to the fourth minus x to the second minus 4x plus 2. And then I'm going to take the minus sign that's here And then we do the minus on the 3x gives me minus 3x to the fourth. Right? The minus on the minus 4x squared becomes plus 4x squared. And then the minus on the plus 3 becomes minus 3. And the reason why is you're subtracting the polynomial, so it affects every term inside it. Is that clear? And then we're just going to combine like terms. So we have the 7x to the fourth and the minus 3x to the fourth. That will give me 4x to the fourth. And then we have the minus x squared and the plus 4x squared. That's plus 3x squared. You have the minus 4x. And plus 2 minus 3 is minus 1. Okay, are we good to go with that? Okay, multiplying polynomials. This is just exactly what we've done here. We have a monomial. Remember, a monomial means one term, right? Times a binomial. Binomial means two terms, right? So when you have a monomial times a binomial, all you're going to do is just distribute that monomial through. So it'll be 3x squared times 7x cubed, which is 21x to the fifth. And then it's 3x squared times the minus 2, which is minus 6x squared. Okay, then we have here in the next example, a binomial times a binomial, right? Two terms times two terms. Got it? Now, I like doing FOIL, right, where you FOIL it out, first, outer, inner, last. Some of you guys I just memorize it as a pattern though. So I'm going to take the x that's in the front of the first group, and I'm going to distribute it through the second group. So x times 3x is 3x squared, and then the x times the minus 5 is minus 5x. Are we okay with that? Then I'm going to take the plus 2 and I'm going to distribute that through. So plus 2 times 3x is plus 6x, plus 2 times minus 5 is minus 10. Then I'm going to combine the minus 5x and the plus 6x, and so you get 3x squared. Minus 5 plus 6, that's plus x, 1x, minus 10. Do you guys recall all this? Is this all a repeat of what you've done? Okay. And then example 4, you can see you have a trinomial times a binomial. Tri means 3, right? Times a bi means 2. And so I'm going to keep repeating. It's the same process over and over and over again. So I'm going to take the x squared. I'm going to distribute that through the second group. So x squared times x is x cubed. And then x squared times plus 3 is plus 3x squared. Now I'm going to take the plus 2x, distribute that through. Plus 2x times x is plus 2x squared, plus 2x times plus 3 is plus 6x. And then finally, I'm going to take that plus 1. I'm going to distribute that through. So plus 1 times x is plus x. Plus 1 times plus 3 is plus 3. Okay, how are we doing? So x cubed right? That's just x cubed. There's no other like term. 3x squared and 2x squared is plus 5x squared. Plus 6x plus x is plus 7x and then plus 3. How are we doing? Could I flip those around and do a binomial times a, right here, can I flip the order of this and do a binomial times a trinomial? Would I still get the same answer? Yeah, you just take the first one and you would distribute it through all three terms, the second one through all three terms, add your like terms, and you come up with the exact same answer. Okay? You get the pattern? Conjugates. So the cool thing about conjugates are, that's what we have here. Bring this down just a little bit. Now with conjugates, can I take the 3x and distribute it here and the plus 2 and distribute it here? Yeah, we totally can do that. Here's the thing though, is that the middle terms will always cancel out with conjugates. Okay, so we can actually shortcut this. And so if I want to shortcut, what I can do is I can take the 3x here and just multiply it times 3x. Well, 3x times 3x is 9x squared. Then I can do the plus 2 here, and when I distribute that through, I'm going to get minus 4. Okay. And that will be the answer. Notice that if you choose to multiply it all out, it would be 9x squared minus 6x plus 6x minus 4. And these middle terms here and here, they always cancel each other out 100% of the time with conjugates. So that's why we can shortcut them when we multiply. You don't have to distribute it through. But notice I can distribute it through. I come up with the exact same answer. Clear? Okay. So, and then here for this next example, method 1, would be to take the 3x minus 5, and since it's squared, you would write it times itself. And you would distribute through like this. I'm not going to go through that because we just did a bunch of examples up above. Method 2 is what I have here to the right, or left, sorry. It's the square to the left, square to the right, double the product, and fight, fight, fight. So if I'm going to square to the left, that's the first right here. The left term here is that, whoops, is the 3x here. And when you square that, oops, let's change the color, there we go. 3x, when you square that, isn't that 9x squared? Are we together? Then square to the right means I'm going to take the minus 5 here, and I square that. Well, a negative 5 squared, isn't that plus 25? Then it's double the product. Okay, so the product is multiplying these two terms together, the 3x and the minus 5. What's 3x times minus 5? minus 15x. This is the product. So what's double the product? Good, minus 30x. Okay, and fight just tells me that I have three terms. 1, 2, 3. Right? Square to the left, square to the right, double the product, and fight. Okay, so this lesson's a little longer because of all the vocabulary. Are we together there? Okay. Now, Pascal's triangle. Okay, I'm going to focus over here. And Pascal's triangle is a cool way of seeing relationships. And so in Pascal's triangle, every row begins and ends with a 1. So the first row, there's only one number. It has to be a 1 because it has to begin with a 1 and end with a 1. Got it? The second row has two numbers. And since it has to begin with a 1 and end with a 1, then it's a 1 and a 1. Got it? The third row, it's a little different. It has to begin with a 1 and end with a 1. But now we've got to come up with what is the middle number right here, okay? And what you do is you add these two numbers together. So 1 plus 1 is 2. And so my second row is 1, 2, 1. That's the third row. The fourth row, right, is 1 and 1, has to begin and end with a 1. And there has to be two numbers in between this time. So we're going to add the two numbers it falls between above it, right? So 1 plus 2 is 3. 2 plus 1 is 3. So 1, 3, 3, 1. The next row has to begin and end with a 1. You would add these together here, here, and here, and so you see 1, 4, then 6, and then 4, followed by a 1. Can you do one more row right now on your paper? And you can check with what I write. Did you guys get 1, 5, 10, 10, 5, 1? Could you keep building if you needed to? Now, here's the cool thing is that each one of those rows is represents the expansion of a binomial. Expansion, right? Binomial is two terms. A binomial raised to a power. So first row right here that we're in, this is row 0. They start counting at row 0. And the reason here is that it represents a plus b to the 0 power. Now, anything to the 0 power is what? 1. And so you can see we have the 1 there. Got that? So the next row would be row 1. And so you can see here that I have a plus b to the first power, right? Because it's row 1. So a plus b to the first power. Well, if it's to the first power, isn't that just going to be a plus b? Right? And if it's a plus b, it's the same, right? A plus b here. The number in front of the first a is 1. The second variable, it's also a 1. 1, 1. Notice 1, 1. Get the idea? Okay. Now, this next row, row 2, which is really the third row, right, represents the coefficients, right, of a plus b to the second power. Okay. Now, remember when you have a binomial to the second power, it's square to the left, square to the right, double the product, and fight, right? So notice here, wouldn't it be a squared plus 2ab plus 1b squared, or b squared? I put the ones in just to make it look nice, but notice here, it's 1, 2, 1. Notice it's 1, 2, 1. Got it? So in row 3, when it's expanding a plus b to the third power. So its coefficients better be 1, 3, 3, 1. And notice that it is 1, 3, 3, 1. Okay. How are we doing? Okay. So let's do example 7 again. It says example 11 again. It's actually example 6 again. So we have here, it says example 11 again. I need to fix that because it's not example 11 again, it's example 6 again, okay? This time we're going to use Pascal's triangle, and if you remember correctly, you look at the power that's here, and it's 2, right? So that's actually, you add 1 to go to row 3, if you remember correctly, right? A plus is row 2, the third row down. Notice that its coefficients are 1, 2, 1. Do you guys see that? So what I'm going to do is I'm going to come down here, and I'm going to do 1, and then leaving space 2, leaving space 1. Now what I'm going to do is I'm going to multiply every single one of those by the first term to a power. So I'm going to multiply all of them by 3x. I'll write it this way first. And since the highest power is a 2, you'll start at 2, and then you just count down 1, 0 for their exponents. Then we're going to repeat the process. Minus 5. And you're going to multiply all these by negative 5 this time. And you're going to raise those to powers, but instead of starting at the highest power, you start at the lowest one and you count up 0, 1, and 2. Now, if I were you, what I would do is I would just work with each term independently and then write them together. So I'll just work with that very first one, this one right here. And so I have 1, right, times 3x when you square it. Isn't it 9x squared? And negative 5 to the 0 power, isn't that just 1? So 1 times 9x squared times 1, that's just 9x squared. Then plus, now we're going to multiply 2 times 3x to the first is 3x. Negative 5 to the first is negative 5. And when I multiply that, I'll do 2 times negative 5. That's negative 10 times 3x is negative 10x. So I could write plus negative 10x or minus 10x here. It's not 10 though. What is it? What's negative 10 times 3? Negative 30x. Good. And then for the last one, it's 1 times 3x to the 0 is just 1 times negative 5 squared is 25. 1 times 1 times 25 is plus 25. Now, this third method of expanding 3x minus 5 quantity squared, is it faster? I don't think it's faster than square to the left, square to the right, double the product of 5, 5, 5, right? In fact, I could probably multiply it faster than going through and doing this method, right? Okay, but notice here, now I'm going to do it with x plus 2 to the third power, okay? X plus 2 to the third power. So if I'm going to do it to the third power, I have to go up here on Pascal's triangle. Third power is going to be row 3. That's this one. It's the 1, 3, 3, 1. And I'm going to bring the 1, 3, 3, 1 down here. I'm going to space them out nicely. So 1, 3, 3, 1. And then I'm going to multiply all of them by the first term, which is the x. So x, 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 and you raise the first one to the third power, and you just count down 2, 1, and 0. Then I'm going to multiply all of those by the second term, which is the positive 2. So it'll be all of them multiplied by 2, and you raise those to powers also, starting at the lowest, 0, and counting up to the highest, which will be 3. Are you guys okay with that? Okay, and then finally, this is, I'm going to do each term. So this is 1 times, when you cube the x, it's x cubed. When you do 2 to the 0, it's just 1, and that just gives me x cubed there. Plus, the next one is 3 times, when you square the x, it's x squared, times 2, that's plus 6x squared. Plus, this is 3 times, this is x times 4, and that's 12x. And then this is 1 times 2 to the third is 8, which is 8. Now, doing the cube, expanding the cube, do you think that's faster than multiplying x plus 2 times x plus 2, and then multiplying that again by x plus 2? It's starting to compete now, isn't it? Right? With speed. And if you have it down, I would say for me, it's probably faster than multiplying x plus 2, x plus 2, x plus 2. If I raise it to the 4th power or the 5th power or the 6th power, it will definitely be faster, okay, than trying to expand by multiplying it out. Okay, so I think right now that that's a good place to stop. I'll make sure in our notes that we have example 9 and example 10 filled out, and so that you can refer back to those.